did in last week in online mode. The online mode was a huge success, and in the second week, we started offline. Today's lecture, the first lecture of today's program will be given by Dr. Uwais Kulza. I'll give you a little bit brief introduction about Professor Dr. Uwais Kulza. Dr. Uwais Kulza is a distinguished professor at Islamic University of Science and Technology in Jammu and Kashmir. He is known for his extensive research and expertise in the fields of nanofluids with a focus. Dr. Uwais Kulza is highly respected academic and published numerous papers in leading international journals and conferences. He is also an active member of various professional organizations and has received several awards and honors for his contribution to the field of nanofluids. Dr. Uwais Kulza is an inspiring figure in the academic community and continues to make significant contributions in the field through his research, teaching, and mentorship. Professor Uwais Kulza, off to you. Yes, sir.
Dr. Uwais, you can start.
Okay, sir. Basically, I guess, okay, sir. Thank you. Myself, Uwais Kulza, and I'm currently the Assistant Professor and in charge of Department of Mechanical Engineering at Islamic University of Science and Technology. Thank you for the introduction. So, without wasting much more time, I welcome you all to the third day of the, in offline mode, to the ATAL Faculty Development Program on Thermal Characterization and Advanced Measurement Techniques, which is being organized by the Department of Mechanical Engineering Department of NIT Srinagar. It's an honor and pleasure for me to speak on this prestigious FDP, which is being coordinated by the Adnan sir and Shahid Salim sir. I am still a student of the Adnan sir. I did my doctorate under the Professor Adnan Prem. I started long back in 2015 and I completed in 2020. So my basically the area of the research was the nanofluids for thermal applications. We did a study wherein we employed the nanofluids for to be employed in the solar reactors. My voice is audible and clear?
Yes, sir. Yes, sir.
Okay, thank you. Thank you for the information. So today I'll be speaking about the nanofluids, their synthesis and the characterization. Without wasting much of the time, I'll briefly take you through the presentation. My contents of the presentation will be briefly introducing the nanofluids, followed by the synthesis, and what are the characterization techniques, what are the experimental methods to determine the thermophysical properties, what are the applications, and at last we will discuss some case studies. So starting with the nanofluids. See, we have been facing a lot of problems with the conventional heat transfer tubes, which includes the basic problem is that we don't have a very good heat transfer coefficient, which actually plays a good role in the heat transfer. If we talk about any thermal applications, we should have a good heat transfer so that ultimately the process and the system is very efficiently. So this term was long back in 1990, while the base fluid or any heat transfer fluid, conventional heat transfer fluid was doped with some nanoparticles. So essentially, the nanofluids are types of the advanced fluid that contain suspended nanoparticles in the range of 1 to 100 nanometers. These nanoparticles are typically composed of materials such as metals, metal oxides, carbon-based materials. So the many researchers have reported that it has been very advantageous to use the nanofluids. So what we learned so far that because of the high specific area and high stability as per the suspensions which contain the micro-sized particles, and the best part about the nanofluids is that we have a greater level of the control on the thermodynamic transport properties, and we have reported that there are the improved thermo and physical properties of the nanofluids. Essentially, what we do is that we have a base fluid. While we dope it with some nanoparticles. Depending upon the type of the application, depending upon the type of requirement, we select a particular type of nanoparticle. So nanofluids have been researched well in last 1 decade. Many new concepts have emerged, which include one of which is the hybrid nanofluids. I guess there's a bit delay on okay, hybrid nanofluids. So hybrid fluid is essentially wherein we have two different types of the nanoparticles doped in the one fluid. These are considered to be the extension of the mononanofluids. Mononanofluids are essentially the nanofluids wherein we have one type of nanoparticle doped in one type of fluid. There are many categories, like we have two types of fluids with one particle, we have two types of fluids with two particles, we have one type of fluid with two different types of particles. So essentially, what we can do, suppose if I take an example, if I dope any heat transfer fluid, say water or any glycol or any ethylene glycol, I dope it with some nanoparticles. Say I dope it with the thermal Al2O3. It's a very commonly used nanoparticle in thermal applications. So essentially, what it does, it improves the thermal conductivity. Say now, for instance, I want to increase the surface tension as well. So I will choose a nanoparticle which will enhance the surface tension of the nanofluid. So depending upon my requirements and depending on the properties which I want to improve, I select the nanoparticle accordingly. So in last one decade, there has been a much growth in the study of the nanofluids and the hybrid nanofluids. Essentially, the hybrid nanofluids are very research, very less as compared to nanofluids. We can see around in 2019, around 6,300 papers were published in nanofluids and around 170, 180 papers were published in under the category of hybrid nanofluids. So I believe this is the area where which has a lot of scope for research. So this is a summary of some basic nanofluids and nanoparticles that have been used in the research throughout the globe. It includes Al2O3, magnetic, multi-volt carbon nanotubes. It includes silicon carbide. It includes tungsten. It includes FMWCNT. It includes CNT. It includes iron, silver. It includes copper. It includes silicon dioxide, and so many combinations. And among the fluids, we have the thermal oil, which includes the thermal VT1, thermal 55, and many oils like that. And we, of course, the water has been researched well under this category, ethylene glycol, and the mixture of all these fluids. So, what are basically essentially the factors which affect the performance of nanofluids? Nanofluids are greatly influenced by the nanoparticle concentration, by the particle shape and size of the nanoparticles, particle material, temperature, and how these nanoparticles are prepared, nanofluids are prepared. These are all parameters which influence the performance of a nanofluid. So going straight away to the synthesis of the nanofluids. The synthesis of nanofluids is essentially done by the two methods. One is called the one-step method and another is called the two-step method. In one-step method, what we do is we produce the nanofluids and nanoparticles simultaneously. That means the process of preparing the nanoparticles as well as the nanofluids are done simultaneously. There is nothing like that we have a first we prepare the nanoparticles and we disperse them into the nanofluids. No. In one step, what we do is that the nanoparticles and nanofluids are simultaneously prepared. So the common methods that are used on the one-step method is a direct evaporation technique. We have a chemical reduction method, we have laser ablation method, we have microwave irradiation, we have phase transfer method. And then the most commonly method used is the two-step method as compared to the one-step method. The advantage with the two-step method is that it's very cost-effective and it's very ideal for the mass production. What we do in the two-step method is that the nanoparticles are first prepared and then dispersed into the fluid. What we do essentially in this case is that we have a commercially available nanoparticles which are prepared by different methods, and then we, based on the requirement, based on the size, based on the shape, based on the concentration, we dope the fluid with these nanoparticles. Essentially, the following procedure is adopted while preparing the nanofluids. First of all, we take the nanoparticles, we weigh them, we weigh the appropriate nanoparticles, and we disperse them into the heat transfer fluid, as shown in the figure. Then essentially, there has been the stability issues. I'll discuss that in the later slides. So essentially, when we dope the nanoparticles into the heat transfer fluid or a base fluid, then we subject this mixture to the mechanical styling. So this step shows the mechanical styling, where essentially we use mechanical stirrers or magnetic stirrers to perform the stirring operation. It has been found that the stirring is not effective as so we need to have some add-on processes which includes ultrasonification. Ultrasonification is essentially the subjecting the mixture to the sonification, which essentially is done by the either by the ultrasonic bath or by the probe sonicator. So the advantage of using the subjecting the mixture to the ultrasonification is that it ensures a high stability, it ensures a uniform dispersion, and then the particles are uniformly distributed. And finally, we have a nanofluid with us. So this is again this is a schematic wherein we show how we have prepared the nanofluids. Then the characterization is of the nanofluids. It is very important characterization. The characterization of nanofluids is basically it includes the process of identifying, understanding, and the properties and characteristics or behavior of the nanofluids. See, whenever we do any fluid with some particles, so we should expect a change in their behavior, in their characteristics, and in their properties. So, in order to quantify that property, that characteristic, and that behavior, we use certain characterization techniques. Characterization of nanofluids includes the measuring various physical and chemical properties such as thermal conductivity, viscosity, surface tension, zeta potential, particle size distribution, and stability. So it's very crucial to understand the properties in order to optimize the performance in various heat transfer applications. See, these are the two images. One is a STEM image, another is a TEM image. This we have used in our study in where we have employed an hybrid AL2 and TiO2 nanoparticle. So characterization plays a very important role in deciding the role, in deciding the concentration, in deciding the shape, in deciding the all performance factors which affect the performance of a nanofluid. Essentially, so the characterization plays a very vital role. So proceeding further in the characterization techniques, what are the properties that we need to understand and we need to learn by means of these characterization techniques? So first thing that we need to understand the surface morphology. Surface morphology is basically how the particles are distributed in a nanofluid. Then maybe at times it undergoes a certain chemical reactions. So we need to understand the composition, then the particle distribution, how the particles are distributed in an nanofluid, whether there is an agglomeration, whether they are uniformly distributed. So we need to understand the particle distribution as well. Then particle size and shape. And among thermal physical properties, we'll be discussing thermal conductivity, we'll be discussing the reversible properties, we'll be discussing the specific heat, we'll be discussing the density. So to understand and to measure all these properties, we have various characterization techniques, which includes the hot wire measurement, which includes DLS, which includes DSC, and then maybe microscopic techniques. So starting with the first characterization technique, we have how in case I am supposed to determine the surface morphology, so I will be using the scanning electron microscope. Scanning electron microscope essentially is an electronic microscope which studies the distribution of the material at the surface. So this is one of the basic and I can say a significant characterization technique that has been used by the researchers all over the world. So what is the principle and what the information I get out of it? See, I just showed you these are the two images. This one is a SAM image. The one on the lower left corner is the SAM image. So what information do we get out of it? Or else how does a SAM microscope works? It basically have a tungsten filament which is being heated and it generates high-speed electrons. High-speed electrons. These high-speed electrons are focused on our sample as shown in the figure. Once this high-speed electrons hits the sample, it produces the various signals. The electrons interact with atoms in the sample and producing various signals. These signals are detected by the detectors, which includes the X-rays, the X-ray electrons, and certain these signals. So these signals ultimately generate an image. Let me go back to this image. See, in this image, this is a black and white image where you can see some dark spots and then you can see some light spots. This basically indicates the difference in the density and in the composition and in how a material reacts to the electrons. So this way we can interpret our SAM image. Another technique is the SAM, which is combined with the EDS. EDS is basically, it helps us to determine the elemental composition in the sample. See, say for instance, I am using a nanoparticle whose composition I don't know. So EDS is essentially used to determine the elemental composition of sample. How does it react? This is the EDS it generates an high beam energy, which is essentially done by the microscope. It's always used in combination with the SEM or FEACM or some TEM or other instruments. So essentially, the high energy beam which is focused on the sample, it causes certain X-rays to be which are being reflected from the sample. These X-rays basically represent the certain element. They have a certain characteristics which are similar to the certain elemental compositions. So based upon the X-ray, the intensity and the characteristics of the X-ray, we can decide that at that spot which element is present. And I can show you this is one of the areas that we did in our study, and it shows a part of the manganese, it shows a part of magnesium. It is basically generated on the characteristics of the X-ray that are being reflected or generated from the sample when we strike an electron beam on it. So one more is the surface morphology, wherein which can be employed by using transmission electron microscope. It essentially one this disadvantage of the STEM is that since we can't go really to the nano level, we are not able to predict the size by the scanning electron microscope. So later on, a new characterization technique was introduced, which is known as transmission electron microscope. Transmission electron microscope is essentially a microscope wherein the space or the image is generated on the basis of the transmission of the electrons through a sample. You can see this is our sample in violet color. When we focus, when we push, when we this through an electron on the samples, high-speed electrons on a sample, the few electrons are passed, few electrons are reflected, and few electrons are reflected back. So based upon the response of the electrons, we have an image. This is essentially on the image on the lower right corner is a TEM image. Essentially, you can see the clarity of the image because it is the property of the TEM which produces the high resolution images. So it's very easy and it has been very comfortable and quite accurate to determine the size of the nanoparticles through TEM image. And it's more suitable for the liquids as well. So it can also provide information about the crystal structure, defects, and the composition of the material as well when coupled with the ETs. Okay, one more important thing is the particle size and distribution. We usually determine the particle size and the distribution by the dynamic light scattering technique. What essentially is a dynamic light scattering technique is that when a beam of a laser light is passed through a sample of a fluid, the light is scattered by the particles of the fluid. Some of the scattered light is shifted in frequency due to the movement of the particles. The shift in frequency is known as a Doppler effect and is directly related to the speed of the particles in the fluid. By analyzing the time-dependent fluctuations in the intensity, DLS can measure the Brownian motion. We have a famous Stokes-Einsteinian equation which essentially relates the Brownian motion with the hydrodynamic diameter. So based upon the hydrodynamic diameter, we can calculate the zeta potential. Zeta potential is basically the potential difference between the molecule and the adjacent layer to it. This DLS. Then it essentially measures the hydrodynamic diameter around the particle, which is based on the Brownian motion. So based on the detection in the fluctuations that are observed in the detectors, we determine the particle size. It has been very useful technique to determine the particle size. It gives a distribution. Distribution as what is the range of the particles, what is the concentration of particles that lies in this range. Say I have a particle, I have a sample which contains say 80 nanometer APS, the average particle size is 80 nanometer. So in order to determine the particle size, so what essentially I will subject the sample to the DLS in this equipment. The Light Scissor 500 is one of the famous equipment that is being developed by the Anton Park. So essentially when we put the sample into it, laser light is impinged on the sample. So depending upon the presence of the particles, depending on the Brownian motion, it undergoes the scattering of the light. So that is being detected by the detectors. So finally, the difference, it helps us to calculate the particle size. Now, one more important is the zeta potential. Zeta potential has been a very important and I can say, very accurate technique in deciding the stability of the nanoparticles. Higher zeta potential is basically the major it uses idea about the stability of the particles. If the zeta potential value is very high, be positive or negative, then it is a stable. If it's below the plus 30 or a minus 30, it should within the range of minus 30 or plus 30. It has been decided that it has been basically well reported that the suspension can be treated as unstable. So our effort should be that we should have a zeta potential above, either above by 30 or it should be low minus 30. So it should have a higher value. So essentially the zeta potential is again measured by the same similar equipment, light scissor 500. It's a combination of it's the equipment which gives us the particle size and the zeta potential. So this is based on the electrophoretic light scattering technique. The principle of ALS is based on the fact that charged particles in a suspension will move under the influence of electric field, and this motion will affect the scattering of light by the particles. See, in this figure, we have a laser light that is by a beam splitter and a modulator, and it's impinged on a measurement cell which contains our sample, this blue color box. Essentially, this contains our sample. So a part of this is being reflected or scattered, and it's combined by it's detected by a detector. So in illustrating, a laser beam is directed onto the sample containing the suspended particles, and the scattered light is detected at a particular angle. As the charged particles in the suspension move under the influence of an applied electric field, the scattered light changes its intensity and frequency. By analyzing these changes, in the scattered light, the electrophoretic mobility of these particles can be measured. This essentially works on the principle of measuring the electrophoretic mobility. That's why it's called electrophoretic light scattering method. It measures the scattering electrophoretic mobility of these particles, and based on that, it gives us idea how the particles, with what velocity they are moving towards the charge, towards the electric field. Based on that, we get an idea about the zeta potential. Essentially, if you look at this picture, the center red particle is a particle with a negative surface charge, and the positive particles that stick around it. Then this gets slightly lesser as we move away from the particle. So the point at which the attraction is felt, this essentially is a zeta potential. So more the zeta potential, more is the particle stable. That means if this width is more, that means the particle is in well contact with the liquid surface. If it's very less, then the particle doesn't have a good bonding with the liquid surface. So essentially what we try to do is we have to increase the zeta potential. So there are various techniques by which you can increase the zeta potential, which essentially includes the use of surfactants, use of modifiers, and different things. They ensure that the zeta potential gets increased. It has a very good bonding with the liquid surface. Okay, now again to introspect about the stability, we have to do some more analysis. So we have something available that is known as spectrophotometry. Spectrophotometry is essentially a technique wherein a beam of light is passed through a sample, then measuring the amount of light that is being absorbed by the sample at different wavelengths. It's based on the Beer's law. See, we have a light source, then we have a monochromator. Monochromator is essentially which can allow us only a one single wavelength, light of one single wavelength. So say I naught is the intensity that is being that's the intensity of the light that is being based on the sample. So IT is a transmitted. So a part of it is being absorbed, a part of it is being reflected, and a part of it is being transmitted. So whatever the difference, whatever the process has been taken, that is being detected to the detector. So finally, we get an idea about how much light is being absorbed. So now, how this is being used as a technique to measure the stability. Essentially, what happens? See, suppose I have prepared a colloidal suspension wherein I have doped the nanofluid with wherein I have doped the base with some nanoparticles. So essentially, when we have doped the nanofluid with the nanoparticles, say, at some point of time, if the particles are uniformly distributed. So when we subject this sample to the spectrophotometry, a part of this fixed light will be absorbed by the solution. Say now after 7 days or 8 days, some of the particles have gone down and settled to the base. So essentially, there will be a clear path to the light, so, and you reduce the absorption capacity of the solution. So they will give a clear path to the light that is being impinged on the sample. So essentially, what will happen? The absorbance will get decreased. So if we compare the absorbance of the 7 days before and 7 days after, it will have a difference. So depending upon the absorbance, we can see whether the particle has been settled down or not. So this is how how it will be used for the stability. And further, if the sample is to be used for the this solar applications, say I have to see what amount of light is being absorbed in what category of the wavelength. So it will be very easy for me to understand the and optimize using the spectrophotometry. Again, we can ensure we can measure the stability by using the by measuring the pH. PH measurement is essentially it involves it uses a pH meter or electrode, which while in the voltage difference between the two electrodes is measured. The difference between the voltage between the electrodes gives us idea about the pH of the solution. This is how we can measure the stability of the pH measurement. See, the isoelectric point is the pH representing the potential is zero and particle carry no net charge. So essentially, we have a higher zeta potential in our samples. Okay, now we have one more technique, that is in order to determine the purity of the sample, monitor chemical reactions in real time. We use a technique that is known as a Fourier transformation infrared analysis. This is a typical graph, which is the output of an FDR analysis. See what FDR analysis does. It again in FDR analysis, it involves passing an infrared light through a sample and measuring the amount of light absorbed at different wavelengths. The absorption spectrum obtained provides information about the types of the chemical bonds present in the sample, such as those involving functional groups like OH, NH, and CO and others. See, essentially, when we subject a sample to an FDR analysis, so we subject this sample to a infrared light at a particular wavelength. At one point of time, it's subject to one particular wavelength. See, as a function of the wavelength, we can see what is the transmittance. So the a particular transmittance value corresponds to a particular functional group. So at a see, suppose this 3150. So at 3150, this it has around the 68% transmittance. So this corresponds to a particular this thing a particular functional group. So these are the two studies have been done. One is with the base fluid GK and another is with the copper oxide nanoparticles. So you can see how the functional groups and the composition have been altered when we have doped with the nanoparticles. So this is important to depending upon the application. Now coming back to the thermal conductivity and thermophysical properties. There are various techniques to measure thermal conductivity. One such technique is the transient hot wire. Transient hot wire technique is a process in which is a technique where we use a heated wire that is immersed in a sample. See, this black bold line is a heated wire. It's immersed in a nanofluid. The wire is heated by passing an electric current through it, and the temperature rise of the wire is measured. See, this has certain features. There are certain assumptions. Assumptions like that. This has infinite heat capacity. There is no thermal resistance. So whatever heat is being generated, that is being sent to the fluid. So we measure the rise in the temperature of the fluid, and based on the particular solution of the Fourier law, and by using this relation, delta T equal Q by 4 pi lambda ln of 4 alpha T by R square C. See, essentially what happens, we will do one thing. This whole term 4 alpha R square C is constant. The only variable is a ln of T, and here is delta T. So we'll measure the change in temperature as with the function of time. So based on a specific solution and slope, we can have the measure of the thermal conductivity. This is a very essential technique, but there are very simple assumptions with these things, that we have to be in a steady state. There has to be no external disturbances. There has been no fluctuations. So essentially, then we can have the accurate measurements using transient hot wire technique. One more technique is the laser flash method. Wherein we use this technique involves the use of a laser to heat a sample of a nanofluid. It essentially consists of a metal disc wherein we focus our laser. For a very short period of time. There is a rise in the temperature of the sample, measured with thermocouple, and then the thermoconductivity of the nanofluid can be calculated as a temperature rise and from the known properties of the material. This is how the laser flash method works. Then the most important is the rheological properties. See, when we add certain things to the some base fluid, say like I added nanoparticles, I added some surfactants, I added different types of nanoparticles. So obviously there is a good improvement in the thermophysical properties. Like we have improved thermal conductivity, we have improved specific heat, we have a good wind speed, and stuff like that. But there is some other disadvantage as well. I can see that there has to be all these increases are also subjected to increase in the viscosity, which is again not a problem actually, but in the heat transfer applications, it's going to increase the pumping power. So essentially, there has to be a compromise between the increase in thermoconductivity and increase in the viscosity. So determining the increase in the viscosity is equally important as other thermophysical properties. So in order to determine the viscosity and other flow characteristics, we use the various rheometers. Rheometers are basically the devices which measure the rheological properties, which includes the dynamic viscosity, flow behavior, and certain other things. So what does a flow behavior include actually? Actually, whether the fluid is going to behave as a Newtonian or a Newtonian or stuff like that. So what essentially there are various types of the rheometers available in the market. So I will be discussing the drag type rheometer. Drag type of rheometer is essentially it consists of two plates. One is a stationary plate, another one is the rotating plate. And between these two plates, we hold our sample. So we apply some torque to the rotating plate and to maintain a certain RPM. So this torque is directly proportional to the viscosity. So this gives us idea about the viscosity of the sample. So it's calibrated and we get an idea how much what is the viscosity of the fluid. So what is the difference basically? What is essentially we could have simply used a viscometer. Viscometer, the difference between the viscometer and the rheometer is that the viscometer is basically it gives you the flow behavior or a viscosity at a particular shear rate. We can vary the shear rate in viscometer. So rheometers essentially we can vary the shear rate as well as the temperature. Well, temperature can be can also be varied in the viscometers, but it gets precise in the rheometers. So one more property important is the specific heat. How do we actually measure the specific heat? Specific heat is measured by the differential scattering calorimetry. It is used to measure the specific heat of the nanofluid as a function of the temperature. This technique involves the use of differential scattering calorimeter. In DSC, the sample and these are basically in DSC there are two pans. One is a reference pan, and another is a pan which contains our sample. So there are two approaches to do it. One is that in order to both are subjected to the heating, and two thermocouples or two temperature sensors are fitted in two pans. In order to ensure the uniform temperature rise in both the samples in both the pans. So what the DSC equipment does, it ensures that the heating is done in such a way that in both the cases the temperature rise should be same. See, essentially what I'm trying to say is that whenever the two samples or two types of samples, one is a sample, another one is a reference. When they are heated, so depending on their composition, depending upon their features, depending upon their characteristics, they will behave differently. So in that aspect, so there will be the different heat requirements. So, but essentially what we are doing now, doing in DSC, we are fixing the temperature. Otherwise, see, depending on the specific heat, depending on the heat capacity, the sample A will have a different temperature rise, and sample B will have a different temperature rise. So, what in DSC does, they are trying to maintain the temperature difference equally and increase or decrease the heating content. So based on that, we get an idea about the specific heat of the sample. This is a very useful technique. It not only gives us an idea about the specific heat, it gives us an idea about the phase changes, chemical reactions, and thermal degradations. Density, again, very important. Density is one of the basic physical properties that we need to understand for this thing, for the performance of the nanofluids. So one of the basic and most popular method is the oscillation method. Essentially, what happens in the oscillation method, we have a U-shaped tube which is filled with the sample. The tube is then set into the oscillation at its natural frequency using a piezoelectric crystal. Piezoelectric crystal is essentially which actuates the oscillation. The frequency of the tube's oscillation is related to the density of the fluid. See, there are one gold light, that's the reference oscillator. Once we fill the U tube with the fluid, and then oscillate it, it goes from its reference position to some above and below positions. So there on two sides there are we have fitted four sensors which essentially measures the amplitude of the oscillations. So depending upon the amplitude of the oscillation, which is directly proportional to the which is directly proportional to the density of the fluid, we get an idea about the density of the fluid. So this is again an Anton-Barr's tabletop and handheld density meters. So we also have a temperature sensor with it. So since density depends upon the temperature, so we get an idea about the density at a particular temperature. Surface tension, again very important, very highly good application. So it basically we use a pendant drop method to measure the surface tension in a nanofluid or in any application for that matter. It studies the surface tension of nanofluids, which is the property of the interface between the fluid and the surrounding air or another medium. Essentially, what we do, we have a pipette or maybe a syringe, wherein we drop a small drop of a nanofluid that is suspended from the tip or a middle of the capillary tube. The shape of the drop is analyzed using high-speed cameras, and which is then by the analysis done by the image analysis software. The surface tension of the fluid then can be calculated based on the shape of the drop, properties of the fluid, and the surrounding medium. How we measure the surface tension in case of pendant drop method. So there has been this is one of the basic criteria wherein we have to measure the performance valuation. Performance valuation is very important and it varies from application to application. We did a performance evaluation in our research. What we essentially did is that we were in the process of developing the nanofluids for thermal applications, for solar applications. They were supposed to be used in the solar connectors. So our ultimate aim was we evaluated physical properties, we evaluated the rest of the properties, we did the characterization techniques, but our ultimate aim was to see how it's going to behave or behave in an actual system, in a real-time system. So what essentially we did, we developed an in-house system wherein we evaluated the performance of the nanotube. What we did, these are the 6 test tube holders wherein we put the 6 different samples of the nanotubes, and we subjected it to some heat radiations, maybe an artificial heat source, and we fitted a thermocouple inside each sample. Then what we did, we measured the temperature rise in each sample. Based on the characteristics of the nanofluid, based upon the absorption capacity, based upon the thermophysical properties, we get different results in each of these samples. Then we interpret those results accordingly as we were supposed to. So what are the applications of the nanofluids? Applications, it includes the heat transfer applications. It has been widely used in the air conditioning systems, in industrial heat exchangers, where we want an efficient heat transfer. The nanofluids have been widely tested and widely used in the solar panel applications, solar PVD systems, as they can absorb and transfer heat more effectively. Biomedical applications, wonderful. The nanofluids are, in fact, the whole nanotechnology is doing wonders in the biomedical applications. It has been very effective in cancer treatment, in drug delivery systems, and encapsulation of drugs with nanoparticles. See, the many researchers or many biomedical professionals are facing the problem to deliver a drug at a particular place. So what they did, they are trying to encapsulate the drug in nano films and nanoparticles and deliver to a place where it is supposed to be delivered. So it has been all possible because of the nanotechnology, I can say. The lubrication applications, as lubricants in mechanical systems such as engines, turbines, they are being used as lubricants. They have excellent lubricating properties, reduce friction, wear on moving parts, which increases the efficiency and longer component life. Environmental applications. The nanofluids have been found to be very effective in water treatment and purification. They can remove impurities and pollutants from water more effectively than traditional methods. And the nanofluids are also being used in nano electronic cooling applications. It also includes energy storage applications and many more such. See, I'll give you a real-time example. Just go back to your home and just see and then use a and check this thing. We use hand wash in our home. See, they have mentioned it on their label that it contains the silver nanoparticles. See, the nanoparticles and the nanotechnology have started to be in our real life. They have started occupying the real-time applications. Before going to the case study, I would like to know if there are any questions. Mohsen sir, am I audible?
Yes, sir.
Okay, are there any questions?
Sir, am I audible?
Yeah, please.
Sir, I have a question with regards to synthesis.
Please.
So, do we add surfactants before adding nanoparticles or after that?
See, this is an experimental procedure, and you have to see what is the aim and what is the role of adding the surfactants. If I am manipulating the fluid properties alone, then it has to be added prior to the addition of the nanoparticles. If the addition of the surfactant is more effective after adding the nanoparticles, then it varies from the case to case. You actually have to see how it works for you. In certain cases, we treat nanoparticles separately before adding them to the fuel. So it all depends upon your requirements.
What is this intermediate we have added? You said
Your voice is not clear.
Mr. Alok, आगे आइए ना थोड़ा सा, so that he can see you. यहाँ पे आइए. थोड़ा सा he should be able to see you also ना. Where's that? Dr. Wes, मैंने आपको बोला था ना, once you finish your presentation, you can come upstairs.
Okay, sir, I have a one case study to discuss.
Okay. So, Mr. Alok, you can ask questions later on. He'll be coming upstairs ना. ठीक है ना? So, Dr. Wes, you can continue, huh?
Okay. So we will be discussing one case study, wherein we will see the synergistic effect of the wherein hybrid TiO2 Al2O3 nanoparticles that have been doped below thermal 55. First, let me introduce you about the thermal 55. Thermal 55 is essentially a heat transfer fluid which is being used in various heat transfer applications, particularly in solar collectors, in heat exchangers, wherein a good amount of heat is being extracted. The best part about thermal 55 is that it has a high boiling point around 300-400 degrees Celsius, so it's quite stable above 100 degrees Celsius. Then we try to improve the properties of thermal 55 by doping them with TiO2 and Al2O3 nanoparticles. First is what we did is that we selected the TiO2 nanoparticles with their size and shape, and similar case with the Al2O3 nanoparticles. They are subject to the ball milling, and after completing the ball milling, we prepared the Al2O3 and TiO2 hybrid nanocarbon. We employed the two-step method into the thermal 55, and we use only this surfactant, and finally we are prepared with the Al2O3 TiO2 thermal 55 hybrid nanofluids. So essentially, we prepared the 5 different concentrations of the nanofluids. We used 0.5 ml for 1 gram of nanoparticle as surfactant. And initially, we subjected the mixture to the magnetic stirring, then followed by a ultrasonification by a probe centrifugator. This is the semi time image. This essentially is around the 80. This picture, the time image has been taken on 100 nanometer scale. So the few particles are of less size and few are in bigger size. So average particle size is around 80 nanometer in this case. So we did the stability by using the segmentation analysis. We took the pictures of our samples once they were prepared after 3 hours, and we let them understood for 7 days. So we can see there was not much difference in the change in the color of the samples, which indicates that the samples were good. They were stable over a good period of time. Then we also did the particle size distribution study, wherein we found that our average particle size was around 80 nanometer for Al2O3, and around 20 nanometer was in the for TiO2 nanoparticles. We also studied the zeta potential measurement. We found is as we increase the particle concentration, the zeta potential got decreased. So essentially, so what does it indicate basically? With the increase in the concentration of the nanoparticles, the solutions tend to be less stable. although it's above 30, so we treated them to be as a stable. So we did the zeta potential measurements after different instants. In this case, it did after 7 days, and with the high concentration nanoparticles, it got reduced to 34.43 millivolts. We did a study on optical properties. We found that the absorbance is increasing with the nanoparticle concentration, so which peaks at around 700 nanometers. So it lies in the visible range. So since we are employing the Miller source vectors, so a good absorption capacity, a good absorbance value was obtained for these hybrid nanotubes. We also this tested the thermal conductivity. We studied the thermal conductivity as a function of nanoparticle concentration, which was found to be increasing with the increasing nanoparticle concentration. We also analyzed the thermal conductivity as a function of temperature. So with the increasing temperature, then the thermal conductivity got increased, and it was true for all the concentrations. We again did a study on the rheological properties. The fluid, the viscosity was found to be independent of the shear rate, which indicates that the flow is Newtonian. As you can see from the figure, that the flow, our flow behavior was the Newtonian. Then we did some tests on the temperature as a function. To determine the viscosity as a function of temperature at different shear rates. So what we found is that the viscosity got decreasing, and it almost reached to the base fluid at high temperatures. These are tested different shear rates. Then we tried to see that there was a viscosity enhancement. Viscosity enhancement was maximum 20%. See, I told you at the beginning that there has to be a compromise between the thermal conductivity and the viscosity. So essentially, there was a around 24% maximum increase in the viscosity at all shear rates. Then the performance valuation, this is what I believe is the one of the good results that we have done, that one of the good works that we have done. So what we found is that the temperature rose in rose slowly, and it reached to a maximum of 156, 157 degrees Celsius in terms of base fluid. And what we found is that the temperature at a particular time was found to be increasing with the increasing concentrations. So we also compared the zeta potential. See, the zeta potential in case of hybrid nanofluids was almost, it came out to be stable in all the cases. In all the cases, you can see in 0.05 to 0.5 weight particle concentration. In all the cases, this orange box indicates the hybrid AL2 nanofluids. So it was found to be all positive, all stable in all the cases. And it got decreased with the increasing concentration. This is comparison with the optical properties with the mono nanofluids and the hybrid nanofluids. The hybrid nanofluids had much more absorbance as compared to the mono nanofluids. We compared the viscosity. Viscosity was slightly less. There was a compromise between the TiO2 nanofluids had the least viscosity. Al2O3 had the maximum viscosity, and the hybrid was somewhere in between. This is the comparison of thermal conductivity and maximum temperature enhancement. Now, coming back to the last slide is the conclusions. Nanofluids offer promising properties applications in various industries. Nanofluids exhibit enhanced thermodynamic properties. Synthesis and characterization of nanofluids are crucial to the understanding their properties and potential applications. With the development of new synthesis methods and advancing characterization techniques, researchers are able to manipulate the properties to achieve specific desired properties. Various accurate and precise measurement techniques have been established. The potential applications of various industries, including energy and biomedicine, make them an area of interest for future research. The study of nanofluids is an exciting area of research with significant potential for innovation and discovery. Thank you. I shall see you in person in the high-tech field.
वहाँ जाके भेजी आपको मैंने yes both sides ये मुझे बहुत से बड़ा बड़ा है so he will be live now here you can ask him any questions all questions in fact in the afternoon he will accompany me to Central Research Center so we have a very excellent technician there he's a PhD he can do all of this trigonometry then can request the cases वो another step was cognitive potential nanotext natural go right now small voilà it was चलिए अब बस यहाँ पे सीधे without using any
So I hope you enjoyed. Was it helpful?
आप सीधे आ जाओ ना हाँ अच्छा so you can ask him questions now
Was it helpful? So any questions from you?
Sir, what is the electropolitics
नहीं यहाँ तो नहीं है
See, zeta potential is very, it's a very complex product. See, when we do particles into the fluid, manifold theta design. So we have essentially negative particles. So अब क्या है कि हम जब zeta potential measure करते हैं, हम इसको इस सैंपल को इलेक्ट्रिक फील्ड में डालते हैं. So now depending upon the charge, it will move towards certain positive or negative. So that is electrostatic. So उसको हम measure करते हैं. So depending upon that, we say कि इसमें कितना effort लगा to come from this place to that charge and low electric fields. And it's 20 time. That is essentially the positive negative part. So this particular resolution depending upon the charge. So इसको कितना टाइम लगेगा कि इस ब्लॉक से मूव करके that's essentially the electrostatic mobility. उसको हम measure करते हैं to get an idea of the zeta potential.
a bit loud खाना खाया है ना आपने breakfast किया है
Sir, आपने कहा आपने discussed and you found out that it was a new food. If it would have been some other kind of food, तो इससे कुछ आपके जब आपने ये सोया तरीके से लगते हैं तो उससे कौन सा
See, मैंने जब अपनी बना स्टार्ट की कि मैंने अभी दो fluid level particles ये सब के composition है some good and some bad. To me, this is
उसना login नहीं चल रहा
I don't want to use it, but कोई escape should have it. So it all depends upon how the particles will getting my point. How the particle is going to have interaction with the fluid over a range of temperatures. So what we did in our study is we tested the nanofluids based on the temperature initially. So what we found is it was so essentially I didn't feel a non-nuclear fluid. So apparently what is actually is how non-fluid how our fluid is going to be ever it's because of sudden turbulence in the system. The particle would have not been in good contact with the fluid. So maybe in non-nuclear the particle would have settled down. So we would not have a good stable fluid. I would not call it a stable. So according to my accounting would have been different. My system would have been different. So हमारा ultimately photo from the that was a bit different. So we may not have achieved that temperature in the fluid. Yeah. Any other questions? Estimation. Okay.
quantity of the
Maybe you can get idea from the literature or maybe
yes
see, we don't.
that means hit and trial test question which configuration works
Second is that using too much of something is not desired. So I say I'll do add more amount of something that will affect the quality. Maybe but there are certain things that need to be taken into consideration. First thing is that if you are using the suffering, the सर्टिफिकेट कौन हाँ एग्जैक्टली अल्ट्रासोनिकेशन से क्या होगा कि आपका पार्टिकल यूनिफॉर्मली डिस्पर्स होता है ठीक है नाउ इट्स यूनिफॉर्मली डिस्ट्रीब्यूटेड now if you add subtractant it the particle gets full
प्रॉब्लम ये है कि जो जीटा पोटेंशियल ड्रॉप हो जाती है
कितना
इतना ज़्यादा नहीं कम हो जाती है तो
it's about 50
हाँ उससे स्टेबल रह जाता है
again depends कि आप stability की टेम्परेचर ले कर सकते हैं if I'm editing for a 1 year maybe I have reached a different proportion if it's
you can think on the you can say the
नहीं प्राप्त कर
ऐसे कौन सा फॉर्म है तो वीडियो
and if we drop the nanoparticles simultaneously move it up so
अब on हो गया
the flow solution is a good technique to have a good stability to have a uniform distribution अभी distribution uniform नहीं होगा so our particles
आपका छोटा रखना है
तो जैसे वो stick हो जाते हैं उनका weight बढ़ जाएगा
अच्छा
the effort हमारे particles that's your
हाँ हाँ वो कर पोस्टपोन करें हाँ पोस्टपोन करके आप मीटिंग
फिर से बताइए
उस पे वीडियो हुआ अच्छा
मैंने
तो वही वाला बड़ा करते हैं ना तो वो ये वाला स्क्रीन बड़ा करके सेल्फ वाला पिन करो
that was period of my study I have to observe the control for 7 days now I can sit for a year and observe it depends on my applications here music कितना आप यूज करना है it entirely depends upon that what should be my period of study
दूसरी मोदी से करना
and you can arrange
ये बंद कर वो बंद कर इसका माइक ऑन कीजिए अच्छा ठीक है
see the problem is I tell you one thing when I was being working in lab I remember we had two particles that as I told you was that's very light go up to the it all depends on nature of the hazardous these all depends to be considered and it again depends on the application if somewhere else I'm in a biomedical application then I have to be very careful you need a sort of problem if heat exchangers in bioreactors air conditioning there's not a problem again I'll say it depends on type of the nanoparticle type of the because we can't give a statement of it your statement that nanoparticles are
अवेलेबल है किसी को फोन कर कोई आ जाओ संभालना है 2 मिनट में संभालना अच्छा ठीक
we can monitor the reaction then it depends if the system undergoes a certain reaction whether that's going to be helpful to me or harmful so we can decide we can decide of course so if there are any other questions my email ID was there so I'll be happy to answer
thank you what a very good talk
thank you sir
so I request now Dr. Mohsin Khan to kindly present a moment of small after now we'll be having a talk by Mohsin Khan. They will be joining us online at 11:30. So in the meantime, we can have them here.
Good morning.
So today we have Professor Andalin Target with us. So he'll be delivering an expert lecture. So Professor Andalin Target is Professor at Head Mechanical and Industrial Engineering Department at Indian Institute of Technology, Roorkee. So Professor Andalin has done his PhD from IIT Kanpur. So he is the first one who has employed liquid crystal thermography for experimental measurements in fluid and heat transfer. So his other fields of interest are optical fluid diagnostic tools, heat transfer enhancement, and thermal conductance. So Professor Andalib will be today delivering his talk on thermal conductance. So yes, he is basically applying advanced techniques in measurement of thermal conductance. Actually, what you have, you have to just measure the interface temperatures at the interfaces. So he'll be sharing his ideas, sharing his thoughts, how we can go about with this sort of measurements. Besides this, Professor Andalib is actively associated with Baba Atomic Research Center, Center for Airborne Systems, Gas Turbine Research Establishment, and Churchill Ballistic Research Laboratories as consultant and research. So if the participants are looking for some networking or some collaborative work, you can contact Professor Andalib. So he will guide you, and you will obviously have a good connection. So today I invite. So with these words, I invite Professor Andri to start his talk on the topic. The topic is voyage across the interface. It's a very uh, poetic theme. A heat transfer perspective. Voyage across the interface. A heat transfer perspective. So Professor Andri Tagi, please go ahead, sir.
Okay, just 1 minute. I will begin.
Yeah.
Are you able to see my screen?
Yes, everything is visible.
Okay.
Everything.
So, shall we start?
Bismillah. You start.
Okay. Already, I think we did my introduction, Professor. Thanks to Professor Adnan actually for such a nice introduction, and I look forward to get be in touch with you all. Okay. So this is the name of my laboratory. That is the aerodynamic visualization and thermal analysis research lab. Okay. I think I will take 1 hour.
75 minutes maybe.
75.
Then 15 minutes for questions. In the end, we
Okay.
ask.
Already those who are new actually for them that might be okay. Already I have shown these slides for showing my interest, research interest. Uh, but those who are new they can note it down. So I am dealing right now with the optical technique, flow visualization, heat transfer enhancement, and all that gas to ventilate cooling, nuclear safety research, inverse problem. These are the broader
research interest upon which I do. As far as my personal acquaintance with the different techniques are concerned, we have the expertise in these kind of techniques: liquid crystal thermography, IR thermography, PIV, flow visualization, and hot wire anonymity and cold wire anonymity. As I think the audience is same or that they are new.
Audience is same. Audience is same.
Okay. Okay. So I will just skip these things already. Okay. Now we will start it from here. The idea of this today's talk is just to inspire and educate the students as well as the faculty so that they can select future course of direction for their research program. So now coming, the title is related with the interfacial heat transfer. So now coming back to the basic concept of the boundary basically. You are seeing the screen in the slide mode?
Yeah.
You are seeing the screen, only one screen?
One screen we are seeing. We are seeing.
Okay. So this is the first concept of the boundary. During my childhood days, basically, I was living inside a village, and there was a long, in front of our home, there was a river actually, that is the Gandak River, and we generally perceive the boundary something like that. Okay, uh, the boundary of the village ends at the bank of the river, and we have a just long boundary. You can see it. This is the our my first imagination about the boundary. Later, when we studied the mathematics as an engineer, then we realized that the next stage comes into picture. We define some region of interest for solving our differential set of equation, and to include that one, we define a concept, and this is typically known as bound. This became our mathematical. That was my first childhood imagination, you can say, or understanding about it. So this is related with the engineering. And then when all of you and all of us see the sky basically, then we understand that it is much more different kind of thing is there. Basically, we are looking for the boundary condition for the universe basically, but ideally there is no boundary. Wherever we feel there is the end, suppose the earth is finishing somewhere during the sunset and the sunrise time, we see that is the boundary. But that is not the boundary. Basically, we can say to the whole cosmic region. Suppose the sun and all the stars, galaxies, they are just one after another. They are coming into picture, and that is boundary. Basically, we can say it is nothing but the interface. Interface of one thing is just finishing. One boundary is finishing. Other thing is getting started. So instead of boundary, we can say that it is the whole universe does not carry any limiting boundary. Rather, these are can be perceived through the different interface. It is only that. Now I will ask that okay, see this first image. This first image, this can you guess it from where it has been? What does it signify? Okay, it is again. It is something like that. There is a boundary. This the lower black side. It is the flat plate over which the flow is taking place. So the image will look, these are the actual experimental data by using the PIV technique. This is showing the velocity patterns, the vorticity, shearing layer and all that. And this is, the bottom is the basically the solid wall basically. So this is first kind of concept of the boundary. This is nothing again another kind of another situation of the image. That is the space station NASA people have taken it. How the Earth will see. This is the Earth boundary and this is the adjacent image. So you see the similarity between the earlier image and this image. Again, it is just looking like the same. Similarly, when we see this is the third class of images, that is when the two surfaces, hot and cold, are met at a single point as a line contact will happen. This is the heated portion of the substance, and this is the cold. So heat is flowing from top to the bottom. Again, this is you can see that. So basically, we can see that it is not boundary. Basically, it is all about all about the interface. And the talk of the today, the scope theme of the today talk is related with the heat transfer perspective, a voyage across the heat. These are just the molecular particles when we will see any object at the molecular level. So at the surface, lot of asperity will be there. So we can say I have come this journey as a journey through the interface. So now it has very enormous practical implications. Just I will summarize one data. The major cost of any of the equipment, you know that all of the engineering equipment are directly, indirectly either the heat producing or heat generating or heat sinking them. So most of the failure occurs due to that. When if you summarize it, it has been found that 55% of the failure, major equipment failure, is related with the temperature, 20% is related with the vibration, and 19% is related with the humidity, and remaining is for the dust. So now you can see that how important is the thermal analysis or thermal failure. That majority of the thermal engineering devices, the failure happens due to the uncontrolled temperature, hot spots, or some thermal failure. Thermal is the basic reason that is leading to the failure. It can be the nuclear reactor, it can be the power plant, it can be the aircraft, it can be anything. So the moment temperature shoot up and it is not conditioned properly, then it may lead to the failure. So to avoid the failure, we have to go for the interfacial heat transfer or heat transfer. So basically, we can say that the interfacial temperature rise led to the failure. Now, before we proceed, this is the microscopic view of an interface. Microscopic view means when we will see the object surface from the top, from the at the interface, the how smooth the surface can be. Suppose it may be a glass. Then glass also at the microscopic level, it may contain at the surface this kind of asperity. Okay? And what will happen when the upper portion, again it can be a glass or any smooth finish, diamond, whatsoever is that, or iron, steel, whatever. It may look rough, it may look smooth. But at the microscopic level, it is all about the pattern of the metal. What happens when the upper surface is heated and lower is at different temperature? The heat will flow through one surface to another through the contact spot. And what happens basically in reality that the contact spot is one of the here actually the conduction is taking place. In between the gaseous particle may occur, or if it is vacuum there may not be any gas, but the through this gaseous particle, the conduction gas. This is the second. And the third mode that is happening basically the convection. If the convection is interstitial space is there, if it is vacuum, there will be no convection. And the radiation. So these are the ways of heat transferring from one surface to the another surface when it is in contact with the other surface. So now when we define the TCC in our EDA studies, we all know that the TCC is nothing but the ratio of the heat flux across the joint due to the temperature. And the inverse, how much resistance it is offering, the inverse of that, that is typically known as TCC. Now, the idea is that in most of the real life application, the interface or this kind of contact comes at in varieties of the places. It can be say you can see that this is the piston of a IC engine device basically. Piston is moving at very high speed. And what will happen? This is creating a interface and that will due to friction lot of heat will get generated there. And similarly in the nuclear reactors, fuel bundles are there. There also a lot of interface are there to avoid to design a cooling mechanism to take care of the accidental scenario postulated as accidental scenario of the nuclear reactor. We need to design the proper cooling. Similarly, the gas turbine blade also it is in contact with. It is in. Are you able to hear me?
Yes. You're audible.
Okay. So this is the interfacial temperature. This inside the uh, nuclear any of the electronic circuit, lot of interface the cooling of electronic package inside. So it is generally estimated the heat flux generated per unit area is of the order of in electronics component, it is of the order of nuclear. That's why here also cooling management is very. You might be saying that these days it is the era of miniaturization. Computer becomes slim and slimmer, the mobiles and all that. So it is packed with varieties of some electronic circuit in different layers, and that's why the cooling interfacial heat transfer study became very. In biomedicine, also biomedical application, when we go for the heat replacement therapy, again it creates two joints, upper and lower. What will happen if the its conductivity, surface area is not in optimum way? Then it will lead to the local hotspot creation, and patient will feel this. So it can give the idea that in this field of study or research, you can say, it is very important. Now, the basic question is that why it is so difficult to tame the thermal power. The idea is that basically PCC is a inverse quantity in itself. Means, what does it mean by? There is no instrument which can directly measure the PCC. Temperature directly we can measure it, velocity directly we can measure it. But PCC cannot be measured directly. So basically what happens, it is a we have to put inside some equation, and based upon the temperature distribution pattern, we can evaluate that. So PCC is a cannot be directly measured, and the difficult part is that again it is a coupled problem. It is coupled between the thermal and the structural problem. Depending upon the temperature, the thermal conductivity is one of the factors which will define the heat flow. And what will happen depending upon the temperature, nature, magnitude, the hardness, young modulus of velocity, all will get changed. It will lead to the deformation. So deformation can be elastic, plastic, elastoplastic, something of that sort. So we cannot disintegrate together. Basically, thermal temperature is affecting the thermal properties also as well as the structural properties also. It is a material property, we can say. So it is a coupled problem, and we have to solve both the things together. And that's why for analyzing the TCC, it is always recommended not to deal the TCC directly in terms of dimensional form, rather TCC should be dealt in the non-dimensional form. This is HC bar, that is the typical representation of the non-dimensional temperature, thermal contact conductance. And here we can see that in HQ, these are this RQ is the roughness parameter, geometrical parameter you can see. Pressure, again it is the coupled problem, it is the function of varieties of that. It is not directly the function of temperature, mind it. Basically, temperature indirectly influences the material and the thermal form. But basically, it is the functional dependency is with the pressure as well as the temperature. So that's why ECC analysis has to be done with the help of dimensions. Now, challenges in ECC estimation. The challenges is that why it is so difficult. The challenges are there with the correct estimate of the axial heat flux across the interface. You can see this is the interface, upper and bottom. And at the how much heat flux is passing at the interface, that precise estimation is very much essentially needed, and that is the basis for defining the heat flux. Next thing is that the precise estimate of delta T. We know that due to the interfacial contact resistance, there is a sharp temperature gradient which occurs at the interface. And as an estimate, I can give you the idea that it may vary up to, it can go up to 20%, 25%. What does it signify? It signifies that within the few micron of the interface or at the meeting surfaces, the temperature drop can be of the order of 20%. Means means that if it is we are playing with 100 degree, means 20 degree centigrade temperature drop not near. If we are playing it with 1000 and 2000, then you can see that it can be 200 or 400. So it is an enormous. That's why this correct estimate of the PCC is very important for any of the companies. So for that, the precise estimate of delta T across the interface is one of the challenging areas. Because what we do, we mount several thermocouples, generally routinely, but at the interface, due to very the microscopic level, it is like that. The thermocouple size can be there, lot of other things, a defect will be there. It is difficult. And the next difficulty is that it depends upon the actual contact area. Just I have shown you earlier, when two surfaces are meeting, only contact occurs at few of the spots. As an estimate, the real contact area is extremely difficult to measure. As an estimate, it is of the order of not more than 2 to 5. Means when two surfaces of say nominal area of the square 1 inch are in contact, only 2% or 5% of the upper and lower surfaces are in real contact. The rest are due to filled with the interstitial fluid or something like that, not in contact. So estimation of the real contact area is very difficult. It is again a inverse problem because no technique can directly measure the real contact. It can be only modeled. That is the thing. And as far as the modeling is concerned, as I said to you, it is a basically coupled problem, and coupled problem means it is computationally very extensive. It may require very high computational facility to solve, and when we are dealing at the microscopic level, each and every aspect is into picture, then it is a multi-stage problem. The program may run for days and days. So this is the challenges in PCCS. Okay. Now, why, as I said, why it is a difficult choice? Because no known analytical solution to it. Multi-scale problem means sometimes we have to see model it while taking through APM or something like that at the microscopic level, and sometimes we have to deal that gross body at the microscope. And existing computer might not be enough in many of the cases. When we are dealing with large objects, say nuclear reactors, turbine blade, the scale of the actual geometry is very high. It is difficult to. Now, the factor, basically, if you will ask, we will ask you what are the factors that directly influence the PCC. So, these are the broad factors. What are the broad factors? Nature of contact. Nature of contact formation means it is conforming surface or non-conforming surface. Means it is directly mating completely or some circular contacts are there something. Second is mechanical loading. It is consistent continuous loading. It is periodic loading, or it is load cycling, overloading, these kinds of multiple factors. Nature of material, as I say, thermal properties as well as. And again, in between the contact between the mating surfaces, it is filled with the vacuum, when no gases are there, or it is filled with the ambient or some specific. Can be carbon dioxide, sometimes liquid nitrogen, something. A lot of things are there. Then thermal load. How the thermal load is active? Means continuation operation for a short duration, thermal cycling, thermal shock, thermal rectification. These are the various factors. So this, what I did it, these are the factors fundamentally that influences. So taking too many parameters, again handling together is a difficult task. Too expensive. We started our journey with one of the very primitive nature of project actually that we did it long back in 2008 with the bar case. That we designed a experimental test rig. A small vacuum chamber was there, and inside that, this was a normal setup. And again, the difficulty is there to control all that parameters. Means we have to inside the gas, vacuum has to be there. Okay. Gas and vacuum inside it will be there, so there should be a vacuum chamber. And again, these are the, you can see from the top side, lot of copper pieces are there just to measure the correctly the heat flux that is passing through actually. And this is the actual specimen, say two surfaces, stainless steel, something like that. As I said, it is the factor, one factor is the load, nominal load, which is applying across the superficial substance basically. From the bottom side, we have the arrangement for applying the load without disturbing the vacuum inside it. And some furnace has to be there so that it can heat from the top. And the load has to be measured, heat flow will occur. So it is a lot of complexities, you can say. And that too, we have to maintain all the conditions very precisely, scientifically in a control. So we did some primitive set of experiments. We did the experiment with glass, copper, and stainless steel, carrying various roughnesses. This is the roughness profile you can say when we do at the nano or the micro level. The interface may look smooth. These are the three kind of roughnesses. We varied the roughness also. We what we did it, we mounted thermocouples from top to bottom. This was with the thermocouples. And at the interface, basically, again we did it lot of geometry. It is the conforming contact or non-conforming, something of that sort. Varieties of contact we have built it. And what we do, we capture the temperature, something like that. Okay, upper surface, lower surface, and near to the wall, whatsoever data is there, we extract it. We know that across the substance, it will be a linear conduction law, Fourier conduction law, to be extrapolated. So with this extrapolation, we find out the, we take the actual measurement, specimen 1, specimen 2, for some particular roughness, for some particular pressure with some material. And we repeat every time we change the pressure, or sometimes we change the roughness, sometimes we change the temperature, something like that, and we find out the PCC. That is fluid polynuclear verification. So with this concept, we started developing, and we did lot of experiment, and basically we created the first phase was related with the database. So we did lot of experiment. You can see that the suppose copper, different pressure condition, brass, again different pressure condition, stainless steel. And we have found some physics behind it and we try to explain it. This was the effect of surface finish. Similarly, we fixed other parameters and we did the loading effect. Means we varied the pressure. You can see nominal contact pressure, just in contact. Some pressure has to be there. 3 it's 2, 4, 6, something we have varied. We did with different roughness element and different material. And then we have drawn that. These are all the means if the material is copper pressure, you can say the different.
PPD and PUT.
Then we have invented some correlations. Correlations means we have non-dimensionalized PCC in terms of dimensional parameter, where HC is taking care of the roughness and conductivity and the material or properties, and E by H is the hardness. And then we have fitted a correlation, and we have found that for the flat contact, this we have proposed some correlation that can be used by the design engineers and they are using it in actual condition. Similarly, we have changed the nature of the contact and linear contact to a direct contact, and we have done with different temperature, the 1, 2, 3, the TCC, and again we have proposed certain correlations. So that exercise we did it, and that has very practical. As I said, the knee replacement joint, it is a line contact, or sometimes when two spares ball bearings are there, it became point contact. So nature of contact also plays a very dominant role, and we did it. Next thing is that it is again a very compressed. It is the directional effect also do exist. Means if the upper surface is copper and bottom is stainless steel, so PCC variation with respect to pressure will be something. And if we change the order, upper surface means heat is flowing first from the stainless steel and then copper, again it will. So some directional dependency also. So this has given a new insight to, okay, this is also one of the way, and that's why we have to be whatsoever data we are generating, it is not like that it is universal, it will change the direction of the heat flow, again the value will change. We did with different terms. Not only that, we noticed the hysteresis also. Yes, some we repeated the experiment. We have loaded it, unloaded, loaded, unloaded, something like that. Some hysteresis has been found, and then after this, we did the load cycle. When we are load, cycle one, and suppose we have continuously loaded and loaded 15 times, then 30 times, 45 times, 60. To do one set of experiment, the whole day gets passed. So to generate, suppose n number of data points, now you can see that how much painful it might be. And we found that if ECC became almost independent after some load cycle, say of the order of 45 load cycle, we found that it became a linear. I mean, whatsoever deformation that became permanent. And that is not going to alter the contact area or something like that. So that gets stabilized. So we have found that effect into picture, that is the load cycle. And as I said, nature of cycle one, it is something later. So that means, so that has given an overall perspective by using a conventional thermocouple based analysis. After that, that I will say that all experiment was the steady state experiment. What we do, steady state experiments are always difficult in that way. We have to go for a long waiting time. Just to get a one temperature, one PCC value. Suppose steady state takes 3 hours, 4 hours, 5 hours. So we have to wait a long, and then we have to capture. I will show you that kind of this kind of temperature. This is a steady state temperature. But we have gone for alternative perspective. So what happens during the transient time? Number one, and is it viable? It is feasible to reduce the experimental time, or is it possible that by using the transient data temperature variation, can we get the steady state conductor value? So we did it. Next phase we did with some transient set of experiments. And in the transient set of experiment, this is a inverse problem, typical inverse problem. In the transient, what we do, okay, don't get confused with the ECC is inherently inverse because directly it cannot be measured. Here we are talking about the inverse heat conduction problem. Means we map the temperature patterns with respect to the time. Say we did the experiment for 20 seconds, 30 seconds, 1 minute, and that we have used as an input, and we do some unknown value of PCC, and it is something better explained with the help of this mathematical formulation. This is typical conduction equation, transient conduction equation, and in which we apply the different boundary conditions and we do this measurement and take PCC unknown value, take some value, and then try to calculate. So with this, we can get the solution, case 1, case 2, and that PCC value, we can find out, okay, inversely it has been by using the 1D inverse. So that may we go to the error also because the quality of data becomes very important. That should be very precise, spatial resolution should be very good. And the other thing is that the temporal resolution should be very good. That is the thing. And then for that, what we have to do, we have to capture the continuous temperature. Suppose you can see that time estimate, these are in seconds. So we calculated the temperature variation with respect to time, and these became the input points, input data for our conduction solution. And then based upon this short duration experiment, say 100 seconds itself, we can see that how the PCC will vary. PCC is varying something of this. In the vacuum we did the experiment, and then with some gases also we did. thereafter, so this became a steady state PCC. So this has given a very important insight by using short duration experiment also. We can what we were doing it by using the LCP in the last class I have done in infinite conduction bodies. Similarly, here by using the short duration experiment, we can estimate the steady state. So we have tested this approach, transient approach, with different materials, say copper, brass, stainless steel, with different pressures, different roughness. We created lot of data. Yes. Okay. Now in all that, difficulty was that you can see that suppose two materials are there, five thermocouples at top, five thermocouples at bottom. If any thermocouple get weird or it is making the noise or some contact problem with the thermocouples is there, so that data will never allow the program to survive. It has to be very good. Stable data. So the people who are working in the field of inverse heat transfer, they know that a single measurement might be a good exercise if that is very precise. So that we cannot deal with too many dependency upon too many sensors basically. So for that, we have developed by using a semi-infinite conduction model, we have developed another app. What we do here is we just one thermocouple data at the interface that becomes our result with respect to time. Okay, upper and bottom, and inside the unknown is our TCC. It became when you will see the equation, it will be by using inverse approach. Basically, we can get this kind of solutions for the semi-infinite body in which everything is unknown except this the unknown is our TCC. So when we do it by using iterative technique, iterative approach, we can get the estimate about. Through this figure, you can understand it much better. That PCC upper value, when it heated, when it is come in contact with the lower body, it will start leaking. It will lose it. And lower body will get uh, heated. So a time will come, it will get distributed. So within short duration, again say 80, 100, we have taken the data and we have estimated the value of PCC for different nature of contact, different material, different roughness. We have again customized this aspect. And we got that you can see it here. The PCC variation gets right. So this will become the steady state. So now what we did is we have finished second part of the journey. Okay, we did the experiment, steady state experiment, and find out the TCC. Then we have moved jump to the next stage by using inverse heat transfer conduction problem by using multi-sensor models. We developed a methodology to estimate the TCC, and then after that we have switched to the single sensor. So now is it the picture is clear, or what we got is that perfectly absolute truth? So this is the famous quotation. I will repeat it here. There is always an easy solution to every human problem. Need plausible possibility. So it might be whatsoever we are getting. It is need. It is giving solution to many of the problems, but may contain some difficulty. What are the difficulties? The important question we have to look for is thermocouple based analysis correct and complete? Yes. It is reliable. It is suitable for gross design. But as far as the limitation is concerned, it modifies the thermal behavior of the system. Especially when we are doing the experiment at very high temperature, what will happen? At the extremely high temperature, lot of thermocouples will carry away the heat. It will modify the thermal behavior, especially at the interface. So that will modify the thermal behavior. It may not be very appropriate. Okay, size constraint also there, and we are talking about the asperity contacts at the microscopic level. Thermocouple has the finite size, and we cannot drill hole just at that without modifying the surface behavior at the interface. So thermocouples are generally of 1 millimeter, 1.5 millimeter, something like that. Poor exposure resolution. That's why it cannot fit the correctly interfacial temperature distribution of the delta T, and there may be, if it is picking in whatsoever we do for the extrapolation, the error can be low. Okay, and it may not be appropriate in the critical application. Okay, like electronic chips and wafer when several electronic chips of the order of say millimeter or something they are stacked. So a lot of stacked circuits are there. So everywhere we cannot mount the we can damage this. Similarly, super lattice, supercomputers, integrated circuits, micro contacts are there, and especially in the non-conforming contacts, we can say when the both the contacts are curvilinear in nature. So it is happening a line contact or the point contact. So it is difficult to mount the thermocouple at it. These are given the insight to okay, thermocouple analysis might be suitable for the gross design, but still we are not able to fit the mechanism at the interface. What to target? Precise estimate at the temperature. Okay, which by which technique? Any technique that should be having better spatial and different. The next thing is that it should be visible, then it is much better, reliable. Okay, it should be non-invasive so that it should not modify the thermal behavior, and it can fit the heat transfer very close to at least extrapolation. With all these things in our mind, we have gone to our journey shifted into third phase. This is the step ahead. What we did is we have tried to implement some optical tools like liquid crystal thermography or the IR thermography. These two set of images you can see that this is by liquid crystal thermography between contact and this is the by using IR thermography. Upper surface is heated, lower is cool. Here also you can see. And we try to implement this technique and get the pieces. For that, again, optical perspective comes into picture, optical accessibility, calibration, converting optical signal or image into the data of the temperature, displacement, lot of other things. So we have modified our setup. Okay, we have provided some optical code, and we did lot of experiments with varieties of the different nature of. Just I am picking one of the neurons, flat, and this curvature we have changed valuation. Curvature 1, R1, R2, R3, different combination we have tried it. And we did lot of experiments by using electric. So this is the third phase of the journey. You can see that these are the actual images during the experiment. We did again. We have to, again, methodology can be transient as well as steady. We started with the most reliable technique, that is the steady state mode, and again under steady state camera, a lot of difficulties are there. So sometimes what happens is within the given heat and heat flux condition, the lower heat liquid crystal sheet may go beyond the temperature range of the sensitivity of the liquid crystal. So we have to select judicially the proper bandwidth of the liquid crystals and then paste it onto the surface so that it can fit that heat. You can see that these kind of different possibilities. And then we have converted these images. We have taken the hue again. You remember that in the last slide, last class we have talked about the different color models, RGB, and that is a monotonic behavior of the hue that varies with the functionality of the R, G, and B together. We have created this two-dimensional picture pattern again by using the calibration. Just what we did it earlier in the when we were doing the liquid crystal. So this has given a very good result. And the best part was that K, why it is very good, K, the spatial resolution of the liquid crystal is of micron, say 8 micron, 10 micron, that depends upon the microscopic size of the liquid crystal particles encapsulated within the liquid crystal. So in that manner, the temperature jump whatsoever is happening from top to bottom, we are up to the last extent at the interface, we can fix the signal steady. You can see that we are seeing that how it is going from top. Okay, so this is the thing, and we did these are the transient temperatures. Basically, how the temperature will evolve. You can see that upper temperature is constant when it becomes in contact with the lower temperature and lower substance, lower melting surface, heat flow will occur and it will get stabilized. It will take a temperature, typical temperature profile for and again temperature gradient and water. These two will grossly follow dictated by the Fourier conduction law. And very important thing is that when we have, as I said, this you can see length scale is minus 20 millimeter to plus 20 millimeter. We are just going to focus this interfacial region, and magnify it. Now the same data has been replotted between plus minus 1 millimeter. You can see that earlier we were assuming that there will be in all of the heat transfer book, we will see that the sharp temperature the gradient happen just linearly, randomly, abrupt. But in reality, it is not physically correct because there cannot be random abrupt temperature. We have noticed that we follow certain profile, curve profile. You can see different combination we have seen. So this has never been captured prior to this era by when we have used the liquid crystal thermography for finding out the microscopic level heat transfer whatsoever is happening to capture that. This was the gross picture, and this is you can see that at the microscope. So we can conclude that we at this gross level it follows the Fourier conduction. Depending upon the conductivity, it will be a slope and it will happen. But at the interface, the Fourier conduction law is not sufficiently able to define the temperature gradient or temperature profile. For that, we have generated some data. And we have identified that we can put three distinct regions. At the interface region, in the one direction, it is a gross region, hot body, and another direction, cold body. So we have done interfacial heat transfer analysis. So you can say at in-depth analysis, and we have especially identified the correct value of data by using this. So how much is that data? Okay, and we did it. You can see it. This was the region, and we have plotted the 2D temperature pattern. We have find out that it is happening something like that. This is one region. You can see that hot body. This is cold body, and at the interface we notice three distinct regions. One, two. Okay. So I am just recapitulating, going back to the fluid mechanics. You all know that when we deal with the turbulent boundary layer profile, when we plot the velocity profile on a in the wall coordinate, we found that, or not even in the wall coordinate, when we plot it, there exists three distinct regions of the boundary layer: laminar, buffer, and turbulent. So we thought it may be something like that. Why not to correlate a unified theory? Just like the fluid mechanics, here also the heat transfer may have at the interface may have three distinct regions. Just laminar, interfacial, turbulent, it was there, something of that sort. So what we did is this has given us a insight. Okay, try to see and plot the temperature profile in the one coordinate and try to see that. Now you can see this is our we have not reported our PhD student. You can see three distinct regions are available. One region which is following linear law. Here again linear law. At the interface there is something. So these three different sub-regions we have identified, and we are of the view that there exists a possible analogy with the fluid mechanics. Just like the fluid mechanics, we can correlate. We should correlate. So we have to work and we have to do experiment with varieties of changing parameters, say roughness, material, body, and repeat this kind of insight or in-depth analysis by using some optical theory. So there may be possibility that some analogy may happen and we can define some theory just like now. So, and just to stabilize that, we did it, the TCC estimation, we have formulated a concept of effective thermal conductivity, taking the intermediate region with some effective thermal conductivity and do it. So, earlier, when the solid is one surface, it is a and effective theory, we have defined some effective thermal conductivity, and on that basis, we have evaluated the CC. So by using extrapolation and by using delta T and by using the effective thermal effect, we have just compared. We found that whatsoever we are proposing, that we have published this paper also. This is a possible one of the better way to deal the interstitial group of correct. Basically, which is very important. Whenever any people, even if he is doing the numerical analysis, if the analysis or correct whatsoever is that, he has to do the value of PCC. Otherwise, the program will not work. And as I said, PCC is inherently involved. So the correct estimate, correct value of the PCC at the interface will lead to the correct solution of the numerical model. So that's why for that only comes with the help of the because no numerical technique, no numerical analysis can correctly label the correct value of it. So the thing is that whatsoever we are looking for, is it possible? Will it work? The law of the ball kind of thing. This experiment we did it was a singular case. So I can say at this stage I am not sure. It requires evidence. Requires evidence means we have to do lot of experiments with the similar approach and then generate the idea and then conclude it. But the thing is that is it necessary? Because many ideas basically in the science, if we were when we will deal with the Copernicus and all that, we know that we were working earlier with the hypothesis that the Earth is the center of the universe. Long time, almost up to 1,000 years, people have used it and predicted many things correctly. Then it changed. The sun is the solar system. It is again. It predicted lot of lunar eclipse, polar eclipse. I mean, lot of models are coming. What is happening basically? It is finding some limitation to explain meaning of the natural happening. That's why we have to keep for problems. It requires evidence. Okay. So now beyond these things, we started, we can say, shaping new field at the IPOT. We started with our journey with a small project with the bar. We took a real life challenge to get the solution for get the value of PCC for the actual scenario of the nuclear reactor, where the nuclear material PP and CP we have taken that as a project so that we can develop some correlation, give it to the bar people, they can use it in their actual numerical simulation, and they can use it reliably. So again, generally the experiment need to be done at say 1,000 degree upper surface may be heated, lower surface will be at room temperature. Every interfacial temperature we were able to create in the lab of the order of say 500 degrees. It was not a joke, easy task. It is not a joke. It was a very difficult. So we have gone through different failures. We designed different furnaces, and the idea was that the furnace should be enclosed, that should be implanted inside the vacuum chamber, so that we can do the experiment under the required set of ambient conditions. In the actual nuclear reactors, basically they fill the reactors with the carbon dioxide due to the inert nature of the gas. So we, for that, we have created the different furnace. We tried, and again, loading has to be applied for the bottom. We have to deal so high temperature, 1,000 degrees centigrade within the laboratory environment. Inside a very closed, special closed vacuum chamber setup. So, lot of failure. Finally, we succeeded, and we have designed a very advanced, high-end test rig for measuring the PCC at height. This is the photograph revealing, and here to capture the high temperature again, as I said in the last class, that LCT is not the right choice. It cannot handle very high temperature. It can handle up to 100 degrees centigrade only. So this time we have procured a IR thermography camera, IR camera, and again IR sensitivity means is that we have to pick the correct camera. Again, the port of this window port should be transparent to that IR rays. That has been especially designed that we have fabricated it. So it was again a very costly, almost we can say 1.75 or 2 crores project was there. And we did lot of experiments just like what we did with the conventional materials, say stainless steel, copper. We did the experiment under the various loading conditions with the PTCT pressure tube and calendar which we were targeted. We developed a lot of database. Again, we have not directly jumped to the transient, rather we have approached with the conventional stabilized technique, that is the STD state. We did the experiment under carbon dioxide environment and under the vacuum environment, so that there is two ways of looking at it. One is spot conductance, another is gap. Means when it is filled with the gas, gap conductance. Otherwise, we generally term scientifically that as the spot. So we have done lot of exercise, lot of experiment at different pressure, and we have find out. And the best part was that we were able to view the thing. And visualization, as we know that, it is gives lot of information and it gives excitation also. We feel that what's going on, we are able to capture. Visualization is a very good exercise, but again, I would like to remind that if fluid mechanics, Leonardo da Vinci, he has visualized the flow pattern coming from the top and is sitting at the bottom. And he has done a very famous painting without any visualization tool. Right now, after hundreds of years, people have captured with the experience. So many people, those who are geniuses, they can imagine well in advance how does the actual physics will look like. It can be the heat transfer or it can be the fluid. He did it. That is a very famous painting of it. And we all know that generally most of the time we people are not genius like the dual we have to depend upon the visualization. In the absence of genius, basically, what we can do, we can implement something. So now we can, I will show you some UV. This is the hot surface is heated at say 500 degrees centigrade, bottom is cooled, and in different configuration. And this right one is with the liquid. This is with the iron. You can see that how the temperature is getting changed. I hope you are able to see the video. It is giving you the heat transfer is coming down and cold, it is getting penetrated, something like that, and it is creating the transient temperature. We have converted all these same information into a higher temperature. For different loading conditions. You can say these are the temperature conditions. These are based upon the IR temperature. Okay? So this exercise we did it for the bar, and what we did it with the different door configuration, different temperature configuration, means interfacial temperature was 300, 400, and 500. Again, four loads we have selected so that we can give a develop a simulation. Okay? And simultaneously we have correlated with our earlier understanding which we got by using the electricity. We have clubbed together all that thing. And in this, okay, one very important aspect is that if when we are implementing any optical tool, the most difficult part was that to get the edge detection. Basically, in image basically in LCD, it is not like that when we pasted LCD, it is a continuous image. So where we are not able to see the edge. So with the help of temperature patterns, we should be able to design if okay, the actual physical edge of the substance is something. So for that, we have used the MATLAB. We have developed some algorithms so that we can correctly pick the edge. Because one surface, when it comes in contact with the other surface, slight displacement of the upper surface will immediately happen. Just the pitch. And that's why it becomes moving boundary condition problem. It was very difficult, exciting, but the results were very promising. That has given us the confidence that whatsoever pain we have to take, that is going to give us the results. So we did the heat transfer coefficient variation with respect to the time, and we find out that. Okay, and as I said, we did the experiment by using IR thermography at different four pressure conditions, 3, 400, 500 degrees there, and carbon dioxide and vacuum. This is the summary of the table. And again, we on that what we started by using the liquid photography. That at the law of the wall kind of thing, we started plotting here also. Our spatial resolution was likely high when we are focusing at the interface. We concentrated on that one and we generated some data. And you can see it here also. Okay, again, it is not very random jump. It is following a smooth variation. This is a smooth variation. So with this high temperature measurements and intermediate temperature measurements, we got some idea. What we are doing on that, okay, it is not like that we are just keeping track with the agency, we are getting some funds and doing the experiment. The basic idea behind it is that we should look for a wider set of database at varieties of temperature. Then only, as I said, if we have lot of database, then we can predict something that will be well validated with the help of this set of data. And that has to be done at wider temperature. Say minus, when you say 10K, means minus 263 degrees centigrade to 1000 degrees centigrade. So again, the best part is that when we deal the high temperature, extreme temperature, it is always difficult. As I said, when we are dealing with the 1000 degrees centigrade, it was very difficult exercise. Similarly, under the spacecraft mission, basically, most of the time, they work at very cryogenic temperature. The temperature is of the order of 10K, 5K, or 20K, something like that. And there again, it is very much prone to the radiation at low temperature. It will attract a lot of heat from the environment, and that's why whatsoever spacecraft mission that need to be simulated at the Earth before sending the satellite into the space. That analysis requires the TCC at low temperature, at cryogenic. So that is again a very valuable information because all that simulation people they are looking for some real experimental data of TCC which has to be well validated inside the lab for that specific material under that loading and the surface density and the pressure. So with that things in mind, we have customized our that setup and we have taken one important additional step. We have procured a GM-based criteria, which was able to give the temperature at the fingertip at the order of say 7. We have integrated with our test string. This is the pictorial representation of a figure of actual setup basically, and this is the complete test string at the so that we can do the experiment at cryogenic temperature. Okay, I hope you are getting it.
Yes, sir.
Now, I will just show you the insight. These are the again lot of challenges. At the cryogenic temperature, difficulty is that materials become very wet. When we apply the load, basically, what will happen? Like deformation will be added, and it was the chances that material will get moved. It will break. So there has to be some. When we apply the load, basically there should be some flexibility with the cold finger of the dry cooler. That's why we designed a special power plates. These plates can withstand the displacement. It can withstand the shock and without disturbing the heat flow. The heat flow it will take the drain out the heat of the interface by using this power plates. Basically, we have designed it. We are looking to get the patent also. This is the things, and we did the experiment of the materials which are generally routinely used for low temperature. The temperature can be low, say minus 200 degrees centigrade, 100 degrees centigrade, minus 100. Cryogenics up to 5 or 7, 10K we can attain now to that. So we did a lot of experiments at cryo temperatures. Again, the same exercise, the roughness and different material, different loading condition. We have took on that exercise and we have measured the surface topography also. And we have used, again, it is a very complex thing. At low temperature, thermal conductivity is the function of temperature. At high temperature also as well as low. So we have to use the thermal conductivity as the function of temperature in our equation. For that, we have used another device to actually measure the thermal conductivity with respect to the temperature. That we have used, that was another task that we have published some paper here with the using of that PPMS machine basically. And that became the input for our TCC. So this is one independent area dealing the cryogenics temperature and later the TCC and thermal. And the best difficult part is that these cryo temperature experiments take long time. You can see that to get the steady state, almost 10-12 hours. Just to get one single step ready, we need to run the experiment for 10 to 12 hours. And we did it with the steady state technique approach, and we have taken different materials with the actual experimental data of the thermal conductivity, and we have recommended some correlation for different. And we have found that just to ensure that our setup is very integrated and it is the integrity of the setup should be very high. So we measured the TCC with the help of standard NIST certified apparatus and based upon our setup. You can see that the variation was well within that ensure that our thermal conductivity TCC measuring setup is very highly accurate with great energy balance into perspective. So we did the exercise with the at different temperature, different roughness, okay? And we generated a lot of database. And we have reported it, this many papers in the cryogenics temperature range, TCC measurement, and we have documented that one, and we have generated lots of data. And then we have developed some correlation. As a design engineer in the industry, people they are not interested in all these insights. They are just interested routinely decide what is the value of TCC, or if it is a function of something, kindly give us the correlation. So we developed certain correlations which are able to correctly predict the TCC within the range of experimental parameters. Okay, and that we have developed it that can be found in our literature, and anybody can use it when he is using high temperature, low temperature, same material. These correlations can be considered. Okay, so now when we are dealing these things from the experimental perspective, these are costly things. We thought, okay, numerically also we should develop a methodology again so that we can estimate the TCC. So one of our students he did the numerical also. So here what was the idea that it was not purely numerical. We actually measured the surface topography by using the skies profile. We take that roughness as the input and generated the surfaces. Say we have modeled 1 millimeter by 1 millimeter square area. Applied the load, and this is the surface generated by using FDP tool at the microscopic level, and by using the actual roughness, it is not random roughness, it is actual roughness. And then the idea was that through numerical modeling, can we get the value of real contact area? That is very much interested. The tribology people are doing it totally, and they are very much interested. They are interested in the real contact area estimation as well as the thermal transmission heat transfer across the near intensity. So we did it numerically. We generated upper surface, lower surface, made it, and then we have find out the real contact area. You can see that the real contact area. We did the grid independence test also, and then we have found out the real contact area with respect to pressure. So basically, you can understand the subject in that manner. The real contact area variation is the indication of the TCC values, because the more the real contact area, better will be the heat transfer. So these are the contact response, what we captured by using our numerical means. This cannot be here, experiment gets failed because whenever two surfaces are in contact, we cannot see through. So the only option here is to go through the numerical approach and get the real contact. That we did it. And then on that real contact area, we took that as the real contact area and we designed some mathematical formula and we predicted the TCC. And then within whatsoever data we have generated at the cryo temperature, we get validated. Now you can see a very good validation for different roughness we got. So we have proposed a remarkably new area of TCC estimation by using the roughness experimental data and converting that into the real contact area and finally estimating the case. And we were, what we did is, we visualized that heat lines, just like our fluid mechanics, say, streamlines. Here we did the heat lines, and we have that gives the insight to what is happening. We try to correlate this numerical heat lines with respect to the actual what we got it to the IR photography. Now, doing all that things from different perspectives, what is the whole things what we are looking for? It is an integrated approach in our lab by us. We are doing the modeling also, computational heat transfer, HCT state, transient heat, a lot of things. Numerical simulation, and we are trying to understand what is happening, what is the real truth. So we are right now we are dealing this subject in greater detail from last you can say almost 13, 14 years. And it is a very difficult journey. I show my this image to my students. The ant is generally known that it can carry the weight more than 500 weights of its own. But she carried concurrently. It is a very hard task. We are also trying to work hard and get the real insight by using the different experimental numerical tools and understand the phenomena of electrification. Okay, and this is how we are finishing our voyage. That I can say that conclusion whatsoever Leonardo da Vinci heat that is moved with the basic DNS model and with the latest experimental tools. Similarly, Fourier has given his in his own graph the heat transfer conduction equation. And what we are doing is we are just going to define it or putting the restriction upon it where it can be used, where it cannot. Okay. So the whatsoever has been the back idea, past idea, it should not stop us to think beyond or to dream about the future so that we can refine our understanding and we can be much more confident what's happening at the micro and the macro. So with this, I will close it, the today talk, and I will just show you we are doing, as I said, probably last time we showed it. We are working with the turbulent flow control. This study, this is theme one. Right now, we are working upon it. It has enormous application. This week, yeah, this was the first week I have shown it to you. Similarly, we have done the co-investigation by PIB also. Then we are working with the gas turbine blade cooling. We have proposed a novel matrix cooling concept that is expected to take care of the future generation by Indian requirement basically. You can see that a typical turbine blade, heated blade, it can look like that. And if it damage, then it becomes something like that. So we are working to get the solution, the innovation for the turbine industry also. For that, we have proposed a matrix kind of a structure, and which can give the better robustness, provide the greater cooling depth, so that it can sustain very high temperature of the engine. Because to increase the efficiency of the engine, one easy tool is that to do the burning at very high temperature, attain high temperature. For that, we have designed a test rig. We completed that project also. And there we have implemented liquid crystal thermography for that matrix cooling rate study. And right now we are doing some fundamental investigation by using the test rate. And what we are doing is we are integrating the flow data with the temperature data. You can see these are the flow data. This is the bottom data, temperature data. Trying to club it together, and we found strong correlation between the vortices formation, which is transpiring into the surface heat transfer coefficient. So these are the our recent area of interest upon which we are working at ITBP in our lab at ATAL. These are the you can see that this is that you can see that. So all this taking place. Recently, we have reported some paper in physics of fluid as well as in nature also. We are restricting that. final publication after the final review. It has been accepted also some paper. And apart from that, we are working with the nuclear safety research also. This is also very interesting, where we have invented a new technique, just like PIB and liquid crystal thermography. We have invented a new technique based upon the laser and the routine camera to capture the signal. Because when we do the actual experiment at during the nuclear reactor, this is a typical example of the fuel metal. One fuel rod is there. At high temperature, it may get collapsed. The kind of accident which may happen in the Chernobyl and Japan and all that. We are trying to experimentally and we track and we simulated experimentally in our laboratory condition. And this is the thing. And we develop because no intrusive technique can be implemented to measure the displacement or the sag or the you can say how much sag it happens because the temperatures are very high. High means of the order of 1500 and 1700 degrees. So we have invented a technique. We have created a laser light sheet. We keep on continuously tracking, say 10, 12 hours. And then when the material gets failed under that due to thermal loading, we took that images and converted into this is the experimental test. You can see that how complex it is. It is a very, it was again a 2.5 crore project basically. We completed this experimental facility and we did some sagging experiment. These are the actual fuel bundles. You can see how does it look like when failure happens. It is just like red hot. It just almost melts. So we created that imaging technique. We published that paper also on technique aspect also. And this has been enormous implication in the nuclear safety research. And apart from that, we are recently working with the TBRA to develop a ultra high speed optical diagnostic methodology using framing camera. This is again a very novel theme of the research. We are going to use a camera with million and billion frame per shot. It might be possible we will do some maybe there also. And we will develop some methodology. For that we are working upon. The whole of this exercise, different themes we are working upon. Right now we are in the submission one of the project of 17 crore with the GPRE. We have established a Center for Excellence at IIT Roorkee as one of the coordinators for that one. And we are going to do that project. And all for all that, these are the real heroes who worked hard in our laboratory last 15 years. You can say most of them are the PhD scholars. We got the thanks to our agency, BART, PTRE, CAPS, and HRD and all that. Thank you. Now it is from my side.
For an excellent talk. So, I request the audience participants, so if they have some questions, queries, conclusions, possibly they would just clarify all these talks. So I'll start. First of all, I'll start maybe then you just. Professor earlier you were talking about liquid crystal thermography. So have you used liquid crystal paint or sheets?
Sheets,
Huh?
sheets.
But sheets, okay, fine. So you could have used paints of the grades of liquid crystal paints in
Yeah,
this.
right, okay, okay. That also can.
That can be also done. Okay,
Yes.
so the temperature range of these liquid crystals then is not so wide.
That was on order of 15.
Okay, that's fine. I said, but can you tell me something about that? You have to just ensure that you are having the proper lightning source there.
Hmm.
Then we can take a good image.
Exactly. That should be the white light source.
White light source. Huh?
Yeah, any light that can contains all the bandwidth of the colors is your complete. That wavelength.
Can you tell approximately? Can you tell me what was the dimension of your optical axis so that you could image it?
What was that?
Dimensions, diameter of your optical axis so that you could image that interface.
Actually, our specimen was of the order of say 1 inch diameter.
Okay.
Or less than 1 inch diameter. Height was 1 inch.
Okay.
Means 2 inch by we have viewed the whole.
Okay.
But with the email was say 4 megapixel or something like that.
Okay. Okay. Approximately, talking about something moving boundary value column. Is those moving boundary value columns similar to what we have in phase change phase change when you have phase changes?
No, no, that was the no, no, it was a moving means the when we are tracking the interface,
Okay,
so due to the effect of the loading condition, some deformation will occur. So it will change the edge space.
okay, okay.
So we were talking from that perspective. It
Okay,
was not related.
that's what. That's one more doubt I have. So you were talking about like then you started with liquid crystal thermography. Then you just also introduced infrared thermography. So
Exactly.
maybe you were working in a higher temperature range of.
No, we have worked with, as I said,
Uh,
we have heated the upper specimen up to 1000 degrees.
okay, okay,
Means at the interface it was around 500 degrees.
okay, okay.
Average.
So
It
Professor
was
Ali,
very high.
okay, 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 Professor Ali, can you tell me something about what was the usefulness of this study? Usefulness. What is the usefulness of this study?
We are solving the giving the recommendation to varieties of the industry, say the mark,
Okay.
the PTRE and all that.
Yes.
They can use our PCC estimate in during their actual modeling,
Okay.
and it can refine their models so that they can better do the angle analysis in advance. For the spacecraft also, engines also, for the PL. Everywhere, a lot of applications,
Okay.
depending upon the material and the requirement, nature.
You want to, one of my participants is interested in asking. Please introduce us. First, you sort of.
Good afternoon, sir.
Good afternoon.
Am I audible enough?
Sure, sure.
Sir, this is Dr. Gurpreet Kaur from Women College for Women Jammu.
Hmm.
So my sole intention of coming to this FDP was to hear your lecture
Okay.
and establish
Thanks a lot. Thanks. Your good name?
Gurpreet Kaur.
Okay.
She's from Jammu. She's from Jammu.
You are faculty?
Yeah, I'm faculty, recently
Okay.
appointed in a government college.
Okay. Do visit us. I will come to your college also.
So it would be a pleasure to us to meet you. So actually we wanted to establish a kind of liquid crystal lab in our college and I need some kind of assistance and guidance from your end.
Sure, sure.
Anything that is required for establishing a lab for the undergraduates, especially for fourth semester students because we are having mandate under NEP to conduct a precursory level of research at the college's level.
You are working in which college? State college or
It's a
NIT?
state college. It's a
State
state college.
college. State college.
It's a
So
state.
I think you can plan a visit or something, some collaboration we can do it, and we can design some small test rig so that you can show your students actually how that photography works. You can come and discuss.
Thank you very much, sir. I'll definitely come to you personally and to have a look at your liquid crystal lab as well.
Sure, sure. It is not liquid crystal lab.
Yeah.
You can say it is an advanced research lab.
Okay, okay.
And the idea is that we have the facility of different techniques in our lab. Liquid crystal thermography is one of them.
Okay. Thank you very much, sir. Thank you.
So anyone want? हाँ, आइए. हाँ. Introduce yourself.
Hello, sir. My name is Kamran. I'm doing my research under Professor Adnan Quyun here in natural convection heat transfer. My question is with regard to since you are applying both pressure and a high temperature across the interface. So initially you start with a particular value of surface roughness and use that for correlating it with the TCC. So my question is that during the application of high temperature and pressure, the surface roughness changes. It changes for
So
all.
it will deform and it will become elastic to plastic.
Yes, sir.
Plastic plastic and finally final plastic deform.
Yes, sir.
It will just merge with the other body.
Yes, sir.
That depends upon the temperature as well as the applied.
So the question is, can you correlate the initially higher value of surface roughness for the, the output that we get? Because
Exactly. That was the scope of the study. That's why initially we whatsoever the measurement, roughness measurement I am showing that was the initial. After that we are not interested. With this initial condition, what was the TCC value? That was the scope of this.
sir, my second question is with regard to measurement. Sir, I'm using actually cavity, and it has a fluid inside it. It's made up
You
of
are using you are using
a cavity, a 3D, a
everything.
cube, for example, and it encompasses a fluid inside it. So what we are facing the problem of measuring the temperature profile within the system. So do you have any idea about how we can measure the temperature? Because we cannot use IR camera over here because the acrylic doesn't.
Cavity, I think, chirography, interferometry, these are the standardized technique to study the convection pattern inside the cavity. It has to be made transparent.
Sir,
I
actually
think
the
this
acrylic is
person,
transparent.
Adnan, may have seen some diversity in IT company.
I've
But
used
that was very
I've
old
used
technique
Srinagar.
actually. Now you can see the things from in a better manner with the color shading and all that.
Anyone else? So, thank you, sir. On behalf of Mechanical Engineering Department and Organizing Committee of this FDP, I'm highly thankful to you for just devoting your precious time for this talk. So thank you. Thank you, sir. So, if you have any questions, go ahead. You can just directly mail Professor Gandhi. He will help you. In fact, I'll tell you something now. Professor Gandhi was the person who introduced liquid thermography to me. So I just visited, I think, way back in 2001 ID conference. He just showed me. I was just Shahid and me. We just saw his laboratory. We were just fascinated by his facility. So we got impressed with him. So we started working in his laboratory. So he is a very helpful person. He goes out of the way in helping people. So you can visit him. You can call him. In fact, you can establish a good network with him. You can think of some collaboration with him, and he can help you at all levels.
Sure, sure, most.
So, Professor Andeep, thank you. So nice of you to be here.
Okay.
Okay,
Over.
goodbye. Oh, thank you. Yeah, okay. Okay. Please. No, sir, you need all registered participants.